Hello, you're listening to Angel Nears the podcast. We're a Silicon Valley community and podcast for upstarts where founders and operators share their firsthand knowledge on how to successfully build and scale your startups. I'm your host, Oleg Kuchikov, and our guest today is Sam Fok, the co-founder and CEO of Femtosense, a startup which is developing an ultra-low-power AI processor for the real-time edge that's designed to make AI processing viable for low-cost consumer electronics. Sam will tell me if that all made sense. I'm excited to bring Sam on to talk about the sparse future of AI powering the inside of consumer electronics. How'd that sound, Sam? And welcome to the show.
It sounded great, Oleg. I'm sure. Thank you for having me on Angel Nears, and looking forward to meeting the audience and telling everybody all about Femtosense.
Awesome. Well, yeah, I'm excited to learn. I typically start these interviews with just a little bit of get to know you with the guest. So start off there. Tell us about your background and what kind of led you to co-founding a company.
Yeah, it's a good question. I guess doing the whole starting a company wasn't something that I really thought about much before starting the actual company. But my backstory, as well as my co-founders' backstory, that we were doing our PhDs. This was at Stanford University. We were doing what's called the Brains in Silicon Lab all together, building AI hardware. And, we're getting close to PhD graduation in 2018. And the AI market, especially for hardware, was, really, really starting to heat up then. So we looked around and, we didn't really see much of anything like what we were doing. And so if we were honest with ourselves, and it was true, the kinds of things that we put in, grant applications, that this technology is going to be more power efficient, lower cost, more performant, blah, blah, blah. Why don't you commercialize that? The market timing is there. The technology is different enough. So that's really what got us to start this company, is really identifying that there was an opportunity, seeing that, if you bring this technology to the commercial world, you can really develop it much more rapidly than you could in any sort of academic setting. And of course, there's the economic opportunity. So that's our backstory. And that's why we started this company.
Can you just expand a little bit? So you were in the Brains and Silicon Lab at Stanford. I guess just tell me a little bit more about what you were doing there.
Yeah, so the Brains and Silicon Lab is in the field what's called neuromorphic engineering, if you want to look that up. But the idea is that there are some, if you really look kind of low level at electronics, at the devices we use to build ultimately computers and all the wonderful gadgets we have, there are some eerie similarities between these electronic components, transistors specifically, and the kind of behavior you'd see in neurons in your brain if you're on the neuroscience side. And so long ago, when people were first starting to build circuits and combine them into bigger systems, they sort of saw these similarities and decided that, well, if these things are similar down at the physical level, transistors in subterranean domain and neuron membranes and their electrochemical gradients, then why don't you build things with electronics that work a little bit similar to these neurons, right? Because if you start with the building blocks, then maybe you could build more interesting things. So this was kind of traces its history back to, Carver Mead. That's a name that would be familiar to anybody doing circuits and digital logic. It's one of the big popularizers of VLSI. So how do you integrate lots and lots of circuits together in a coherent manner with principled rules, so you can really scale, right? How do you get to 1 trillion transistors? Like you're not gonna do that by hand. And so this other branch of neuromorphic engineering was another one of the brainchilds from that line of work, or from Carver and his group. And that's where we kind of came from as a lab. So the idea is that if you can make electronic circuits work very similarly, like maybe follow the same governing differential equations as a neuron would, then it becomes just a question of how do you arrange them together to create, interesting intelligent systems. So it's very weird from a circuit design perspective. It's very far from how computers are, most all built today, but it was different. And so that made for very interesting research and was sort of what we worked on as co-founders while, PhD students. We were building a system called BrainDrop, which is fine. You can make little circuits behave like neurons in the differential equation sense. But then the question is, well, how do you get it to do anything useful? So we were working on a system that you could impose a higher level of description of the behavior, maybe some other kinds of differential equations. And then there was an automatic way of piling that down to, thousands or millions of these biologically similar neurons, but without having to do it by hand, right? That was that project. So we did that for our PhD, and that's why we said, okay, this stuff is pretty different. Why don't we commercialize this? And that's Femtosense.
And Femtosense was born. So tell us, what was the problem you're trying to solve for your user, or what's the seed idea for Femtosense?
Yeah, the main angle is that, I guess you got to this in the initial tagline. These AI algorithms and applications, they're very interesting. Things like ChatGPT are grabbing the headlines. Before that, there was DALL-E. Before that, there was GPT-3, and et cetera down the line. You go all the way back to 1960s or 50s if you really want to, take these neural network sort of apps and their history. But one of the problems is that these things are pretty heavy duty, right? Like you're gonna, especially these more recent models, like you deploy these in a data center, right? And you got to cool the thing, you got to spend a lot of money on energy, and you look at how efficient a human brain is, and it's pretty far off what we're doing in electronics and what the biology does, right? So there seems to be a lot of at least a proof of existence that it is possible to do compelling, have some manner of intelligence, how you measure that. That should be able to be done in a much more efficient, from a power and cost perspective, than what we currently have. So, and if you can do it more efficiently, then you could say bring something like ChatGPT into smaller and smaller form factors, which can then deliver value. It's just like when computers started, they were the size of rooms, and now we all have a computer in our pocket, right? And it's by making things more efficient, and that means you can shrink them down. That means you can take them more places, and that means you can do more applications, which ultimately are what people pay for. So, that was the angle of saying that if you can fundamentally make a more efficient AI system, then you can take it to more places that other people can't do, and you can similarly realize the value from doing that.
When did you decide to go after hearing and hearing aids?
Yeah, that's a good question. There's a few angles you can answer this in. One is just historically, the kind of systems that we were building, back in the lab were suited to time varying signals and speech and audio, and is, by definition kind of happens over time, right? In contrast to something like saying a picture is a cat or dog, right? Like you don't have, if you can do that in a video, but fundamentally that's kind of a static problem. So the initial kind of technology that we did, which is quite different from what we're doing today, we had many, technical pivots along the way, is, was sort of already on that route. So that's one angle. You can say like kind of where the development came from, and, what was seemed like a good fit. I think the other angle you could say is, well, the vision market is quite crowded. There are a lot of players there. And so, where do you want to create your beachhead, right? Do you want to, play where Redis is playing? You might also say that the market there is bigger, but you're going to have to pick some sort of beachhead market. And so do you want to go there first, or do you want to go there somewhere else? And so we thought, audio was also nice from a strategic perspective because it wasn't as sort of crowded with other players. And it was a little bit more opportunity to get differentiation, because that's absolutely one of the things you need as a startup. And then, from there, you can, of course, grow into some of these other areas.
Okay. Well, I'll tell you another good reason to get into hearing. Hearing loss affects almost 0.5 billion or 500 million people globally. However, out of those 500 million, only 1 in 6, about 17%. However, only 17% or 1 in 6 of those affected adopt hearing aid treatments. The WHO estimates untreated hearing loss costs $750 billion a year in lost productivity and downstream medical care. What would you say are the major factors that affect, low hearing aid adoption rates?
There's a lot of them. I think maybe fundamentally it is a challenging problem. So, as opposed to like vision. So, if you have short-sightedness, nearsighted, or farsightedness, you can sort of solve this with a lens, right? That's what glasses is. Hearing is a little bit more there's a little bit more processing behind that. Like it's sure there are certainly cases where you have literally lost the hair cells that will listen to vibrations in the air, which is sound. That's certainly there, but there's also a perceptual component of that. How does your brain process it, or how does the cochlea in your ear process it, right? And so this has made it a little bit hard to simply just quote replace some functionality or add a simple corrective thing. Like human hearing is quite complicated. And so trying to create these products and hearing aids that fix or correct any problems people are having has been hard. just to put it very simply, it's a hard processing problem. It's more than just trying to amplify some of the tones of the hair cells that you've lost. You can actually look at some of the emerging research. It's also how do you sort of pull out what you care about from the soundscape and not pay attention to everything else. Like that's not really a physical problem. That's a intelligence problem, right? And so these hearing aids, they have deployed classical digital signal processing algorithms in the past to try to approximate and pull out the kinds of things that we're actually interested in hearing and remove the background. But there's a lot of room for improvement. And so this is where AI can come in to address some of these classic old problems of plucking out signal from noise, but now with a new spin. But then the limiting factor is, well, you're not going to put a big GPU on a hearing aid, right? These things also have to be very small, very power efficient, and so this is another reason why this is hard. And they can't be too expensive because they're already super expensive as is. A few $1,000s each, and then if they're covered by insurance or not, you're talking about a hard sort of product market fit as we currently have.
Well, thanks for unpacking that. Let's talk more about this kind of speech and noise problem. But what is it in general? Talk about the speech and noise problem, maybe from like a technical perspective.
We spent some amount of time, getting this podcast set up, making sure that you had clean, you could hear me clean, you could hear yourself cleanly, and a lot of that stuff was sort of so that we don't get any, random doors closing or people walking by or babies crying or whatever, right? So we could do that with a podcast, right? But, people don't live in podcasts much as we might like. We go out into the world where, you have no control fundamentally over all the various things around you that, go click or clack and or even other people, when they talk, right? And you're not trying to pay attention to all that. In fact, if you tried to pay attention to all that, you'd probably lose your mind. It's just too much sensory overload, right? So we are always trying to kind of focus in on some things that we care about. And that's the challenge, is how, as a piece of electronics, do you extract what you care about and kind of leave behind everything else? So there's a lot of ways to describe it, but I think that's that's maybe in simple terms what I would say.
You get to the heart of it. Yeah. How do we separate that signal from the noise, or how do I filter the important thing from the noise? How do digital hearing aids do this today, right now, in a commercial sense?
Yeah. I mean, there's of course, like any mature industry, there's a lot of tricks, things that people can do. These mostly emerged during just classic digital signal processing, heyday. There's a few. So some of the techniques are, sort of take a statistical sampling of sort of your soundscape, and then throw away more or less the average, because you call that the background, and then anything that's different from there, like when you say certain words, let that through, right? Like there are gaps between the words that I say, right? And so if you can say on average that I'm not saying things, and you could get a baseline of that, you could subtract out that and sort of let me through. So that's one, is kind of adaptive way. Another way is, well, if you have multiple microphones, you can kind of add or subtract these microphone signals together, so you can actually sort of directionally steer a beam to where you're listening to. So this is what a lot of devices do, like AirPods kind of do this. They will listen sort of straight in front of you and create a virtual microphone that is only sensitive to in front of you. This is another thing that people can do. And then there's even more basic things that you can do. Say, well, when people are talking, let's say I'm interested in speech, you can't generate all, tones. Human speech is a certain frequency band, so anything outside of there you can throw away. And there are these are just some of the techniques. There are probably a lot more sophisticated things, a lot more simple things, but all of these, their common thread is like they are kind of approximations to try to capture what designers might think you care about. But fundamentally, there's no sort of meaning attached to that. And, the follow-up question is like, okay, so what do you do different? So this is where, again, artificial intelligence comes in, because just like in the image world, where now you explicitly label like a cat image or a dog image, and you say, please distinguish these two, you can now, for sound samples and examples, say this is an example of things that I want to let through, and examples of things that I don't want to let through. So you've attached meaning now to those sounds, and this makes it a little bit closer, perhaps, to what extracting the signals that you care about, because you can explicitly tell the system and train the system to learn what those signals are and what they are not.
It sounds like a great application of AI, right? But how about performance? How does this perform when compared to other solutions that are out there?
Yeah, I think it's quite competitive. This is a newer technology, so it's always under development. But for example, I will some of the things where these classical algorithms don't do so well is when there are sort of, let's say you're doing the adaptive stuff, when there are transients, right? So I have a little piece of metal here, right? So I tap on the table. I think you could probably hear that, right? So those kinds of things, they will get through your adaptive algorithm, just like your speech got through the adaptive algorithm. And actually, if you're talking hearing aids, the whole point of hearing aids is to amplify and correct for hearing loss. So you're amplifying these impulsive noises, which is exactly what you don't want to do. And that's part of the reason why folks with sort of current technologies that aren't super sophisticated, that's why they don't go to places like restaurants or those kind of settings, because every time you set your cup down or your fork touches your plate, there are these kinds of noises that come through, and it's just not a pleasant experience, which is that's a shame, because that's exactly what you don't want people to. You don't want people to stop going to social settings. You want them to continue to engage and be part of healthy, active lifestyle. So that's kind of how the problems with the current algorithms and handling transients translates to the bad user experience, and then ultimately translates into worse health outcomes. And so, yes, with AI, you can label these things. You could say, hey, I understand this is transient, and also people are transient, but this is a fork, so please don't let the fork sound through. Please just let the human through.
Where do you begin with deep learning techniques?
In general, it really does, at least in today's widely spread algorithms, it comes down to having those examples of saying, okay, well, if you have data that is, what we call labeled, you say, okay, well, here's examples that are, cats, dogs, or fork sounds, or car sounds, or people sounds. You start with that, and then you will architect some neural network approximation of biology, but there's sort of, it's grown into its own field, and then you iteratively, train the network. And what that means is you give it examples of what is good and what is bad. And, when the network gets it right, get a little bit of reward. And when it gets it wrong, it sort of loses some of that reward. And it's just trained to maximize, or it is what your goal is to maximize the performance on the tasks. And so using the magic of calculus and chain rule, you can propagate all those errors, those correct signals and incorrect signals through all of the various parameters and knobs of the neural network, right? And you can they can tell you which way you should adjust things so that it gets it, a little bit more right each time. And you do this enough, and that's how you build your algorithms in a much oversimplified way.
So that is, it's kind of getting into my next question, which is like, what happens during the training phase, and then, after, once your model is trained, what else happens? Like you mentioned labeling, but can you go into it? How do you specifics? Like, how do you train these algorithms? How do you clean that data? How do you choose what kind of data you're working with, and then what do you do after?
Yeah. The data question is a fundamental, you could say, pain point or requirement of, the popular AI models these days. So a lot of what you see out there deployed is kind of defined by, where data is easily accessible. So, for example, if you can scrape the internet for all of your data, you could probably get a good set of data there. And so for this particular application of, extracting speech from everything else, you can get a lot of examples of people speaking from the internet, and you can also get a lot of examples of other sounds. And so, that's how you would build your data. And then in terms of the sort of neural network training and infrastructure. To be short, you use the software packages that PyTorch, TensorFlow, JAX, whatever your preferred framework is, you will use those to describe your neural network architecture. So how do you combine neurons and their connections together to create this massive structure, which then you train, right? And so training is roughly, as I talked about before, where you show it examples of good and bad. You get an objective to try to maximize, and then whenever it gets it right or wrong, you use, again, you really use the software to do this, but, and the underlying math, what you're doing is you're taking the derivative of the error with respect to, the various intermediate values of the network and the parameters of the network. So you're just propagated through the network, and those tell you, sort of in which direction you should move things to, minimize the error and maximize the objective. Maybe one level of things that I haven't talked about is, you probably do want some significant compute to back this stuff, because you're probably going to want these days, more or less, you're going to use some GPU to go through lots of examples very quickly, and do these fine tunings, these sort of small incremental changes in parallel and in rapid succession. So as you get to larger networks, yes, this is when you get to requiring more and more GPUs to train, and yeah, it can be costly depending on how big a thing you want to do. Like I don't know what the bill of electricity or GPUs or special purpose hardware it took to train some of these large models. Not to mention all the salaries of people who are developing and iterating on it. But I'm pretty sure it's quite up there. But you can create baby networks no problem on laptops, or spin up a cloud compute instance. What have you. That's well within tractability.
Yeah, you can, the listener, like it's literally out there, open source. Very cool. Okay, so, these techniques, from my limited understanding, they've achieved good performance in research settings, but they haven't really been deployed too effectively in hearing aids. We mentioned earlier, 1 in 6 people that's afflicted is really making use of hearing aid treatment or hearing aids. If we have the technology, why aren't people using it?
Well, so there's a few layers of technology, right? Sure, there is the kind of algorithm and application layer, right? So yes, we have that. That's kind of what you said with the research, right? So the research shows that yes, you should be able to do this, but a real bottleneck is, how do you actually implement that on the real physical product that has, constraints like it has to be small, lightweight, the battery is only a certain size, it has to last for, a few days. It has to be cost effective, right? That's a challenge, and that's sort of the technological gap that Femtosense is more or less designed to try to address, right? So again, it goes back to that very early point about making AI more efficient, right? So yeah, if your algorithm has billions and trillions of operations and things to store, that's hard to fit in a small product, right? That's just physically, you can't fit it, let alone support it on the battery that has your battery would burn out in no time at all, right? So these sort of just engineering challenges, right? They really are practical limitations on what is feasible in those kinds of small form factor, products, right? And so this is why you still see a lot of these classical algorithms, more or less dominating the world, or the world of hearing, because these newer AI approaches, they're just too heavy, right? They just cost too much energy. They're not fast enough, or too much space with the current hardware. So with our hardware that we build, we make that feasible, right? Within the reasonable constraints of product design, right? So if you can reduce the energy by, 10 times, 100 times, okay, those translate directly to how long your battery is going to last. If you can shrink the sort of silicon footprint by 10 times, you also bring down the cost, and the sort of form factors also become possible too.
So this is like the swap balancing act. Do you want to talk about what's in there?
Yeah, size, weight, power. Sometimes they'll add a C, so size, weight, and power, and size, weight, area, power, and cost. These are all things that if you are building a real physical product, you have to deal with, for better or worse, because we're in a physical world and there are costs associated with things. So yeah, as you squeeze. We're not in the metaverse yet, and maybe everything is going to be gravy there, and then we can really let loose on our creativity. But for now, we live in the real verse, meatverse, and you have to satisfy all these constraints really, like to make a compelling product. It's like when cell phones were first developed, they were like bricks, right? And as a consequence, maybe they didn't have the widest adoption they do now because it's practically it costs probably a lot more than effectively it costs now. Who's going to carry a brick around next to their head? And how do you manufacture lots of these and get the demand? So all of these things matter for the product developers. And but if the product developers have more efficient building blocks like processors or other materials, then they can enable more compelling products, which then drive adoption, which then reduce the cost because of the economies of scale. So yeah, things are all tied together, and it's a wonderfully complex sort of product development cycle.
Really interesting. What would you say the most important constraint is for speech enhancement?
For the AI-based speech enhancement, I think it is the power and speed and size. For the hearing aid world, the things are already kind of expensive, so maybe that's not the most constraining. But power, like you don't want your hearing aid dying right in the middle of a conversation. That would be bad. People kind of expect these things to last at least a day, if not a few days, on one charge. So you don't have that much power you don't have that much battery juice to spare. Speed, this is another thing that's very big. So I'm not sure if this recording platform is doing any noise reduction, but platforms like Zoom, Microsoft Teams, Google Hangouts, they're all doing this kind of noise reduction. But it's okay if there's a delay between, a little bit of a delay between when, say, I say something and you hear it, because we're not face to face. So tens of milliseconds, maybe even 100, depending on your internet connection, of delay in there, it starts to go into uncanny valley, and it also becomes sort of distracting because one, it's kind of like I see you saying something, but then I don't hear you for like half a second. That would be weird, right? I would be distracted by that. You can also get some echo kind of going on too, and so yeah, it's harder. It's a harder problem, right? Because you have to do this processing, but you have to do it in, say, 5 milliseconds instead of 50 milliseconds, right? So now your problem is 10x harder, right? And remember, don't forget you had that battery constraint at the beginning, right? So these two really conspire to preclude these artificial intelligence workloads or applications from being deployed in the hearing aid world.
So if that's the case, why is now the right time for your company to deploy some of those solutions?
Yeah, so why now? Because our technology is available. But, to go a bit into the actual technology that we're using. So, from all that research that we did way back in PhD land, we're not taking that exactly and using that. We're taking a couple principles from that, right? So this will, I guess, be setting some technical context for what we actually do and why this matters to those products. So Femtosense, we're all about, sparse math processing acceleration, as well as sort of what we call near memory or distributed computer architecture approaches, right? So what that means is that, okay, so, we talked about how these AI workloads have, millions, billions, trillions of things going on, right? Every time you query these algorithms, like a lot of stuff has to happen. And, what you can do is train these networks so not all that has to happen, right? One of the things that is not as common these days is that beyond just incentivizing your neural network to do well on the task, you should also tell it in its objective that everything it does and everything that it stores is going to have some cost, whether it's time, energy, or area, right? And so when you make your neural network kind of aware of this stuff, right, it can be like, oh, okay. I will make sort of judicious use of the parameters, the weights that connect neurons together, the times when neurons activate together, so that I'm not doing all the possible work that I could do. I'm only doing a very small subset of that. And so we found that you could eliminate up to 99% of the work that a network has to do for a given input without really impacting performance. And also you can eliminate, say, 9 out of 10 sort of pieces of information that the network actually has to be physically stored, right? And so this basically lightens up the neural network. It makes it so that you're only paying, 1/100th of the energy cost or 1/10th of the area cost, right? And by using our hardware that can actually exploit that in the neural network structure to work more efficiently, this is how you can bring yourself to within the kind of battery budget that, say, a hearing aid would have, the form factor that those packages demand, right? And then, of course, enable these features, right? So, it's a combination of these algorithm approaches, telling the neural network like, hey, everything you do is going to cost something, and then building hardware to actually exploit the structure of the neural network after you've done that procedure. That's our take on how you make these workloads more efficient and actually deploy them in these small devices.
Talk about how you achieve best-in-class performance in speech enhancement.
So this is tied to those approaches I was talking about. So it's not surprising that as you make bigger and bigger neural networks, that these things perform better and better. But then, of course, the cost of deployment goes up as well. So if you have a way of deploying the neural networks for a tenth of the cost or a hundredth of the cost in terms of energy, area, money, or time, then you can deploy much more interesting kinds of applications, or achieve that best in class performance. These days we have the wake up words, right? You could do hey Alexa, hey Google, hey Siri, right? These are all that's kind of pretty common, sort of out in the world, sort of in the edge. That's what it's called. But that's been around since like 2015, right? And one thing you can ask is like, why are those sort of the limit of applications that these small products can do? And if you trace it, it's because it's very expensive from an energy and money and time perspective to deploy these algorithms on the existing processors. So Femtosense, we build a new kind of processor so that you can run these efficiently, and so this is how you can enable these best-in-class performance.
And I know you're out of a lab, but this kind of feels like a silly question. Like, is anyone else doing this, I guess, is my question. And really, I want to know, like, what's unique, what makes you stand out from the crowd. But, I understand you're kind of working on the bleeding edge of technology here. Is anyone else doing this?
Not in the exact sort of formulation that we're doing. I mean, there are degrees of similarity. There's certainly, people have certainly recognized that, okay, so, GPUs have really popularized or help enable the deep learning revolution, right? When researchers recognize that, it's like, okay, the kinds of neural network algorithms are actually, fairly well suited to a GPU, computer architecture, you could do something quite interesting. So that's what really kicked off the deep learning revolution. And we've kind of taken that step a little bit further. It's like, instead of just trying to shrink down what fundamentally is a GPU, which is what a lot of companies are trying to do, we're kind of saying that, well, if you make hardware just for AI that can work in a certain way, then you could do even better, right? It's always this match between, the physical hardware that you're running on and the workload that you're trying to support. That's where you can make things really efficient, right? And so, the space of there are a lot of companies trying to do accelerators, but there's not as many that are trying to do both development at the kind of algorithm level that other people are working on, as well as kind of simultaneous development at the hardware level. And this is where we kind of can stand out, is that we are just as much a chip company as a software company, as an algorithm development company. We do the full thing because that's really how you can squeeze out the efficiency you need to make this practical to deploy out in the world. I think a lot of the maybe competitor companies they're really at their heart and soul just a chip company, right? So a lot of teams we've seen have sort of come out of the chip industry before, where there was very much a divide between, you are either a hardware guy or you are a, software, person, right? To be more gender agnostic, right? And so they don't really think across all of these layers. And what our angle is like, we're like, if you can make changes in the algorithms that existing hardware can't take advantage of, well, you could do something pretty interesting there, as long as you also do the hardware, right? So, and by doing this kind of vertical integration, that's how we compete in terms of performance, and then all that swap-C stuff that we were talking about before.
Who are you building this with? Like, who's your team? And were you always on both the hardware and software side?
Yeah, I mean, it is a complicated world when you do decide to play in all those areas. But our team, spans the whole gamut. We have people who are doing the chip design. We have our own custom architecture. We have our own custom digital logic. We do our own layout. We work with partners, of course, to manufacture. We are, what's called fabless model. Like, we don't literally manufacture the chips ourselves. We just design them. And then looking up from there, we also have, a software team that builds compiler, because without software, your nice fancy piece of silicon is really just a pile of sand or a paperweight. So, you don't want that. You need to build the real tooling that makes it, gives a nice developer experience. And then that's not just words. Like, we also have our AI developers as well, who are building these kind of algorithms like the speech enhancement, right? So who are using the tools that we also build to, take their AI model descriptions and map it down to our custom instruction set, figure out also the, which parts of the algorithm, or figure out which parts of the algorithm go where, because it is a distributed architecture down the hardware level. And so I think, if you meet people from the company, you'll find that they tend to be able to think across multiple levels, because that's kind of required when you are trying to build these vertically integrated systems. Is like, you can't sort of silo yourself in one place. Yes, you do have to be good at a certain task, right? But in order to make reasonable decisions in a timely manner, you do have to have, if not, awareness at least of what's above you and what's below you, but also have some understanding of kind of the full stack system.
But talk about some of the key milestones. Like, the company's been around since 2018. It's pivoted a few times, I believe. So what are some of the key milestones that you achieved along that, 5-year journey to this point?
Well, I guess we can start with the pivots. So, when we started the company, yes, we did start with more or less the technology we developed in the lab. And, I think about a year in is when we decided that, well, what makes for good research technology does not make for the best or the most practical, commercializable technology. And so, we're in the lab, we were doing, if you want to get technical jargon, we were doing, subthreshold analog circuit design. We were doing asynchronous digital design, where there's no clock anywhere in the chip. And we were working with, spiking neural networks at the algorithm level. And all that is sort of well and good. But we found that was, rather difficult to match with kind of the commercial demands that we were seeing from, prospective customers, right? Prospective customers care about, how reliable is the system. Like, it's very different from getting, one system to work and then characterize it and publish and then graduate from getting 100 million systems to work kind of consistently, right? So that's one. Also, the programming model of the spiking neural networks, it was, the performance wasn't quite there compared to what else existed out there. So even if you could claim more efficient operations, I mean, really, you should be controlling for performance, right? Is it more efficient at the same performance? And so, sure, there is some nice biological justification for using, spikes at the circuit level, but we found that wasn't really helping us in the tasks, right? And not to say that whole approach is wrong. It's saying that there are some good principles from that sort of design style that were applicable to technology that sort of existed, namely, the sparse math and the sort of distributed computation. So why don't you just take those and put it in a standard digital flow where there is a clock, and you can work with algorithms that people, pop out of PyTorch and TensorFlow. Like, why don't you do that if you can get most of your gains there and kind of start there, and then you can always come back to the more researchy stuff when it has developed a little bit more, or for whatever reasons the timing seems better. So that was our big pivot, big technical pivot from asynchronous digital plus subthreshold analog spiking to synchronous digital design with programming frameworks that's compatible with the common machine learning workflows, right? While still embodying lots of the principles that made the original system efficient to begin with. So after that, we I guess the next milestone, we got to our FPGA prototype. So this is sort of hardware prototype. We were able to execute our Series A fundraise. So we closed that out this last October 2022. And and then we got to the first, real hardware using this new technology. So we got our first batch of silicon back, around November last year, 2022. And we used that to do real demonstrations of these kind of AI speech enhancement algorithms at, for example, CES is where we were last demoing it. And, now we are gearing up and working with, all of the various companies that have gotten interested in this sort of technology to really, build them into proof of concepts, into evaluations, and, really test it with their users with the target of going to mass production in, as soon as Q3 of this year.
What kind of partnerships have you been building? Talk about some of them.
So we work, can't name names, but we work, across the board in terms of the consumer electronics space. So any companies building, of course, we already mentioned the hearing aids, but the true wireless stereo earbuds is another area. Consumer electronics, anything in your home that you want to, say, control with your voice, that's something that's becoming more popular. We also, and so we work with both the people developing the products as well as the suppliers of those companies. And then we're also working with other processor companies to, potentially take our hardware design and integrate it into their existing kind of main application or host processor to enable larger scale AI. So everything from chip partners to sort of electronic supply chain partners to the actual product developers. We're partnering with people or firms across the board there. We're definitely a B2B play. So, hopefully you'll see some of our features that we enable in products soon.
What can you say about the business model and how you make money? I know you're kind of pre-revenue at this point, but what's the at least the model?
Yeah, so there's a few go to markets. One is go to market with the chips, right? So we got our silicon back. There are definitely companies for which this makes a significant differentiation in their products. So building these chips in volume and selling them is as simple as it gets. There are also the other customers who are the chip developers themselves. So working our designs into their designs, there's a standard IP licensing kind of pathway there. And then there's a little bit of, because we develop the applications, we also are able to license those as well. And so we either partner with firms to port some of their applications to our hardware, or, we also have our own application offerings as well. So it's three things. It's the software, the hardware as, hard silicon, and then the hardware as a design, which we integrate in other hardware.
What's the most important lesson you've learned so far as a founder?
I think it is being responsive and really listening to like, what the market is telling you, but, at a granular level, that means what sort of the customers are telling you. When they are, when they seem to hesitate at certain things, like, that's always something that you may want to spend some, mental cycles thinking about or, ask about, right? And this is a lot of how we did our big technical pivot, is by sort of, thinking about what it would actually take to integrate with the customer's stuff, talking to them, figuring out like, okay, well, why are they, hesitating or not? And, this is, I don't think, I think that as, startup founders, you absolutely have to listen and adapt and respond to what your customers are saying and thinking, or you sort of have to think about what they're thinking a lot, because, you're everywhere. We're all in the business of, making money. So who is going to pay us if not willing and able customers?
I got one more bonus question here, Sam. You said you could stay a couple extra minutes. What's your highest high and your lowest low so far as a founder?
Highest high? I guess, it's getting I was about to say it's getting our silicon back, but I might say it's getting our silicon back and having it work when it turns on, right? And it sort of behaves the way that you expect it to behave. That is a big stress relief. It is just sort of inherent to this, the semiconductor industry, that when you press sort of compile or deploy or manufacture, right, you're waiting like 3 months before anything comes back, let alone testing it and stuff, right? So, in software world, you can compile and iterate quite quickly, right? So that's, that is a huge risk. And so that's a huge relief when you get over that hurdle. Yeah. So that's, I would say, is the biggest high. But, I think that there'll be higher highs than that, especially as we start to really engage with customers and see their prototypes kind of make it to real user testing and see that, okay, it really delivers value. I think that'll probably be a much higher high. And then the, lowest lows, I mean, the economy is all these headwinds. And so doing fundraising in these environments was certainly challenging. So, finding the right partners who we're able to work with, that was certainly a search. It wasn't sort of days of free money, but we were able to get through that. And so, we got to our silicon, and now we are getting our first engagements.
All right. Well, that's very exciting. And again, congrats. It sounds like it was challenging, but you did secure the bag, so to speak. Before we go, what's the best way for listeners to reach you, learn more about Femtosense, and if you have any kind of calls to action here, now's the time to mention those.
So we're B2B, right? So if you are in, firms who develop these kinds of electronics, please do reach out to us. We are spinning up engagements now. You can be reached. My email is just sam@femtosense.ai. We also have our sort of open email of just hello@femtosense.ai. So either one of those, I'll see it either way. And look forward to finding good partners to work with. And, even if you're not in maybe a firm that's developing products that could use AI, definitely be on the lookout for these kinds of features. And develop kind of an expectation that products should be smarter and more responsive to people as people sort of naturally behave, right? That's ultimately kind of the whole AI value proposition. And so, yeah, if people want it, then it will get built.
Awesome words. All right, we're going to end the show there. If you liked it, please subscribe wherever you do listen to podcasts and leave us a rating. Sam, thanks for joining the show. We appreciate your time, your expertise. It sounds like you're doing some incredible things. So we're excited to see where it goes.
Great. Okay. Thank you, Oleg. And hopefully our audience had learned something today.
I'm sure they did. All right. Thank you.